So we're going to go ahead and start dealing with some application pieces of trig today. And this is the one thing that we haven't really dealt with, is how to handle problems that that aren't just, here's the triangle, here's the drawing, go give me, you know, this is just more what happens out there in more of the quote unquote real life situation, which again, I know this is not the real life that most of us lead. You know, most of us aren't walking around with theodolites and survey tools. I get that. It's not name tag and hairnet math or you know, or that's my joke, by the way. Think about that one for a second. Anyway, but it's a little higher in the kind of application. But so we've got a fire ranger here that spots a fire from a 73-foot tower out in Yellowstone National. And she measures the angle of depression. Now, right off the bat, that tells me something. So we have a situation where there's a tower here, right? And where is the fire? Now, where do people look when they're depressed? How are their eyes? They're kind of downcast, right? So here's the thing. When you say something like this, the way the math lays out is you start with the idea of it being horizontal. And if you're depressed, then that means you're going to look down. Does that make sense? Your eyes are downcast. Elevation is to be like a basketball player elevates. That's to look up. Again, it would be from this horizontal looking up. And so there's a fire over here. And I thought about trying to draw it, but I know better. It won't look decent. And so this person is sitting up here at a 73-foot tower, looks down at an angle of depression, definitely not drawn to scale, of 1 degree 20 minutes. Now we want to remember something. What was a minute? Do you guys remember how we did that? That was the first lesson of the semester. How much of an hour is a minute? 1/60th. So this is 1/20th of a degree plus 20/60ths of a degree. Because 20 minutes that's how we kind of did it. Remember, degrees to minutes to seconds. So I'm going to go in here and do 1 plus 20 over 60. Now, I think you all know what that is. That's 1.3. It shouldn't surprise anybody. I'm going to store that. So I just have that in a moment when I'm going to use that. And notice, is this in radians or degrees as the way the problem is phrased? It's definitely in degrees because it says so. So let's make sure that in our mode, we change into degrees. Now, every year I have a few students that find themselves partway through the test, and then they have this panic. Oh, crap. My calculator's been in degrees this whole time. How much of this next test is going to be in degrees is very, very little. It will predominantly be in radians. You have to remember to switch back and forth. That kind of frustrates people. So we have this 1.3, actually, excuse me, 1.3 with a line over it, degrees. And what they want to know is how far is it from the tower to the fire out here? So what is this distance right here? So the way I personally like to do that is I'm going to call this distance x. That's what I want. Now, is the distance x right along the air right here the same as the distance along the ground right here? So I don't really need to draw it down here. I could draw it up here. And do we know what this distance is right here? 73 feet, sure. So what trig ratio would that be? Is that a sine, a cosine, or a tangent? SOHCAHTOA. Is it opposite and hypotenuse, cosine adjacent and hypotenuse, or is it a tangent opposite and adjacent? It definitely is a tangent because what's not labeled? See how the hypotenuse is missing? Not there. It has to be a tangent. So we can come in here and say then that the tangent of 1.3 degrees, now keep in mind on my calculator, I'm not rounding it to 1.3. I can put the line, is defined as opposite over adjacent, right? And so we can either cross multiply and divide or whatever we want to set up. That's fairly simple idea. But ultimately what it comes down to, if I cross multiply, the x's up here and then I'm going to divide, right? So what's left? let's just take 73 and divide it by the tangent of 1.3 with a line over it, which of course I called A, so I didn't have to type it over again, right? You guys cool with that? So how far is she away from this fire? So keep in mind units, 3136.378 what? Feet. So she's a little more than half of a mile away from that particular fire. And boy, I tell you, with the fires that we've been having, if you're within a half a mile of fire, you better get out. You're gonna have a problem pretty quick because those things seem to jump quick around now. Which is interesting. You know, you guys only can see what you have seen in life, but were there fires when I was a kid growing up here? What do you think? Well, yeah, there's always been fires. Are they different? Oh yeah, they're very, very different. And climate change is certainly part of it, but you know, the forest, I mean, they don't want to say that, but forest mismanagement has been a significant portion of it too. If you get dead trees in a forest, what do you have? You have fuel. You have a fuse. It's ready to go. And there's this bark beetle that's set into our forests that kills trees. And so we have literally in California tens of millions of dead pine trees. Would you ever like light up your Christmas tree like at the end, you know, boom? Yeah, you've seen that probably. Some of you have, and that's what our forest does because, you know, I don't know. The sad part is, yes, are there animals that find home in those dead trees? Yes, but unfortunately, once they hit, somebody lights a match to one of them, then those animals are dead too. So I don't know. Forest management is a big deal. So anyway, so let's take a look at the next one. So this one is a slightly different story. Why don't you guys see if you could do that? I hope you guys can kind of follow that idea. This is actually, what is this thing right here? That's the Space Shuttle. Yep. And that's been out of service for quite a while now, which is kind of sad because that was a really, really cool feat of engineering to make a reusable space vehicle. So why don't you set that thing up and see if you can solve how far that is off the ground, its altitude above the sea. Let's try to set it up first. Sine, cosine, or tangent, what do you think? It's a tangent, sure. That's going to be the tangent of 17 degrees is h over 12. This is being measured in what? Miles. Yeah, the space shuttle is not 12 feet off the ground, off the water, or you better get out of the way. It's going to probably kill you. A lot of mass coming down. Those are not small ships. What's left? So this time over here, I had to flip it over and divide. What do I do this time? Just multiply by 12, don't I? So as soon as I multiply both sides by 12, does the mode matter? Sure does. Again, I already checked on the last problem, but on a test, if you're going back and forth, because that does happen frequently, please double check that. So 12 tangents is 17. You should have found that it was 3.669 miles. And you should be aware that on, how high up is 3.669 miles? Any feel for that one? Yeah, we're talking way the heck up there. We're talking 19,000 feet. Do you guys know where big jets fly? International flights, 30,000. They're up there. So this is actually high, but it's definitely one of those things that you'd want your air traffic control to know about because you don't want to accidentally have a space shuttle take out a passenger jet. But do you guys know why we used to at least fly them out of Cape Canaveral, Florida? You guys know why that is the case? Is it because of the water? It's not a bad one, because if you crash into water, that's a little bit safer than anything else, but it's actually kind of cool. My father-in-law for a while actually he's a petroleum engineer, but he actually spent a lot of his time not just engineering, but actually supplying fuel to different places. And one of the things that he did is he supplied fuel to SpaceX. And so he was engineering the idea of getting the rocket fuel to SpaceX and having their flights be ready to go. My father was a pretty freaking smart cookie. He really is. Anyway, but at the time, SpaceX was launching their satellites off of a floating platform in the ocean right on the equator. Why? Now think about this. What happens if you take a slingshot and you go like this? What happens? What does the rock on the slingshot want to do? It wants to launch, right? So the faster you go, the more force it is to launch, right? If you put something down on the equator, something is already moving around, and it's moving on the longest radius that you can put it on, therefore the most force. Therefore, what does that do to the amount of fuel it takes to get it off? It takes less fuel to get it to launch. So the further towards the equator you go, the less fuel. So why do we put it in Cape Canaveral? It's the furthest south point we have in the United States. Plus, you also have the water. I think maybe you were the one that said that. Somebody said water, but both of those two things together are really important. However, what happens if you get water and fuel? Does that do good things for engines? It creates some issues, doesn't it? Right? Yeah. So as it turns out, SpaceX had that, and they finally abandoned it because having your fuel tank floating in the ocean. Now, they worked past that, and they did, but it was very, very expensive to always going through and refiltering and filtering and filtering this very, very high grade rocket fuel to make sure that there was no even tiny, tiny, tiny microscopic bits of water in it, because that would foul the launch. So they kind of went away from it, and now they're doing more of the southerly launches. What I'm a little surprised they haven't done is bought some land down, in Ecuador or something like that, but they haven't. So we're going to go a little bit further. So this next one is a little harder. So these last two problems are a little rough. I will just say these are not your trivial little questions. So we've got this barn roof, and it has an angle of 15 over here and 15 over here. Actually, this one is easy. I was thinking they were different. And it's 73 feet across. And so what is the height of the vertical center post? So right off the bat, considering that it is isosceles, I think we could probably very quickly discern something. What is going to happen right here if I want to look at this singular right triangle? What's that distance going to be? It's going to be half of 73, isn't it? Because 73 goes the entire span. So we're talking 36 and a half. And again, I want to know what the height of that center post is. But, the reality is in many cases, do you think the farmer might need to know what that is as well? Now, that's a pretty significant piece, because if you were to think about what would happen if you were going to try to roof this thing, you would want to know what that length is so you could actually find the rake right here times the distance. That's what you call on a roof, is the rake of it. And anyway, so I think I'm going to find both of those. Let's find the height of that center post, but let's also find that distance. So if I was going to find h, what ratio would I use? You're going to notice tangent shows up a heck of a lot, doesn't it? I mean, because in many circumstances, you want to know the height of the balloon or the height of the plane. All of those things tend to not need the hypotenuse. So that one is pretty easy. Very similar to the last one, 36 and a half times the tangent of 15 degrees. And we're talking a height of 9.780 feet. Now, how could I go ahead then and find x? the actual length of that roof, which would tell me like how much tin it would take to like roof it, or maybe how much tar paper that I need. What do I do to get X? Use the cosine. I like it. So if we did the cosine of 15 degrees, that would be the adjacent over the hypotenuse. And I do like that. Now, in this case, one of the strategies that I hope you guys see is if I cross multiply, I'm going to use kind of a new term that I haven't probably used with you guys before, but it actually is, honestly, it's a basic math thing. But see how these things are kind of far from each other? If you cross multiply, you can always do this. These values in mathematics are called the extremes. They're far away from each other, and you can always exchange the extremes. You can just flip-flop the two of them. If they're on a diagonal in terms of how you set them up, you can reverse those two or reverse those two without any penalty. And so I actually really like the fact that you said use the cosine. This would be a massive roof. But what is another way we could have found X? We could have done Pythagorean Theorem, couldn't we? So on a test, would it be intelligent for us to check our answer back with the Pythagorean Theorem? I think that might be pretty smart. So let's just do that real quick. So I know that if I took 36.5 squared and I added it to this 9.780 squared. Now is this really 9.780 or was there more of it there? There was more. So keep in mind, I may not get this perfectly, but I should get darn close. And then let's take the square root of that. On a test, that took me so little time, but it would tell me that I think my answer's checked out. Now, why do I actually like the fact that we didn't do the Pythagorean theorem early? What if I had made a mistake on this and I used the Pythagorean theorem? Then both answers are wrong, aren't they? In this, in both cases, all I used was given information, wasn't it? You guys cool with that? All right, now, let's go ahead and look at the next little piece. So you're walking towards a building. And isn't that nice? So this is you. You're down here. You're walking towards a building and view the top of the building up here at an angle of elevation of 12 degrees. Okay, so hopefully that makes sense. We're sitting here about like this. We're looking at the top of the building at an angle of elevation of 12 degrees. Then it says you moved forward 50 feet. By the way, this is no joke. This is a tough problem, so kind of be prepared for this a little bit. So we moved forward 50 feet, and you stopped again, and you remeasured. And what's going to happen to my angle of elevation when I get a little bit closer to the building? It's now what? Bigger or smaller? Definitely bigger. As you get closer, you're going to look up that much more. And it's increased to 18 degrees. Now it says, assuming that survey tool, notice the person is bending over a little bit. Have you ever seen these kind of tools like this? Like, it's called a survey, kind of a survey tool. Some people call them a theodolite, I think, if I'm remembering correctly. But what I want to know is how tall is the building? And you might be like, isn't that kind of silly? But you can't always get really right next to a building. Maybe it's on the other side of a fence or something like that, but you could actually figure this stuff out without ever touching the building. And so here's what we've got. So let's figure this out. Do we know what the height of the building is? No. So let's call that X, because that's the piece of information that I'd like to know. There's another little piece that I don't know, is that when I moved forward, I got a little bit closer to the building, but I'm not there. So I know that there's some separation between myself and the building. Are you guys okay with that? So this is kind of strange. I have how many variables in my problem? 2, which generally in math means you're going to need 2 equations. Okay. So with that in mind, let's go ahead and start right here. And let's look at the tangent of 18. Now, Please don't assume that that means every single time it's a tangent in these applied problems, but the ones that I picked out were, because that's just kind of what naturally occurs. The only ones that I've seen that aren't is like, you ever seen the big towers, like the cell phone towers and stuff like that? They put them up on mountaintops, don't they? Or like hills, so that you get that broad view. But what if you're on top of a hill? One of those buttes, like Tustin Buttes, has a lot of our stuff on it because it overlooks the big Sacramento Valley. But there's a lot of wind up there, which means it'll sway. So you put support wires that are called guy wires, GUI, guy wires. And so the length of those guy wires would be the hypotenuse. So sometimes the sines and cosines are going to come in that place if you're wanting to find the length of the wire. But frequently, you just have the distance here and the height. So this would be x over y. Well, that's great, but that doesn't really do it, does it? That doesn't really give me what I need. So what about if I ask you about the tangent of 12 degrees? What would the tangent of 12 be? Now, tangent is opposite over adjacent. And so if we kind of went like this and just thought about the beginning of the story, what's opposite the 12? It is this x. And what is the adjacent on that big fat triangle? Y plus 50. You got it. Now that's a little bit of a bummer because now I have these two equations, but they're a little complicated. I'm going to go ahead and cross multiply, which should not surprise anybody. Y plus 50, tangents of 12 is x. Sorry, my name is Dan. So when I sign things, tan is hard for me to write. It becomes my signature, just muscle memory. So my tangents always look like my signature. Sorry, I can't stop it. But I've got two equations. What do you notice? What is something that naturally happened here, which is kind of cool? This dude is equal to x. What's that one equal to? What can I do then if they're both simultaneously equal to x? Can I just bring those two together and say these two things, y tangents of 18 is y plus 50 tangents of 12. I mean, it just naturally happens, doesn't it? Which is kind of cool. But that's a little bit tricky because I now need to figure out some way to separate them. So this actually was, I laid the foundation for this problem last semester when we were dealing with some crazy log problems. And I don't know if you remember those, but we did some crazy log problems where we did the same thing. Because I want to get y by itself, but notice that y is on both sides of the equation. What do I have to do? I need to get them on the same side together. So there's y's over here, there's y's over here. I got to clean my room up, clean up my business. Let's bring these over to this side. Now, as soon as I do that, I don't think any one particular part of this problem was that hard. It's just the sum total adds up to a bit. What do you notice these both have in common by design? They have a y. And anytime things have something in common, then that means we can factor that. So if I factor out the y, we have pretty much our solution. What's left to solve this problem for y is I've got a number here, right? What is all of this? So if I could divide these two numbers, will I then know what y is? That's kind of complicated, but it's true. So let's see what happens. I'm going to go ahead and I'm going to take this 50 tangents of 12, and I got 10.627. And then I'm going to divide it by parentheses, tangent of 18 minus tangent of 12. And when I hit enter, I've got 94.585. 94.585 feet. Now, By the way, I'm going to store that because I'm actually not done. Because I did not set out to find y in this problem. What did I set out to find? I set out to find x. But look right here. If we know what y is, what do I have to do now to find out what x is? Plug it in. I need to take the y value that I found, 94.585, times the tangent of 18 should be that x, times the tangent of 18, and I got that this building is 30.7 feet tall. That's x. No, it isn't. Reread the problem and tell me what I forgot. Oh, because my surveyor didn't want to lay on the ground and put his eyeball on the pavement. That would be gross. You know, he's going to put it up on the thing. So what do we have left to do? Add what? 4 feet to it. Oh, there we go. So the height of the building would be 34.732. So the height is 34.732 feet. Okay. And that's kind of the story. These are kind of tricky, but you can kind of see how that is. Let's just say that I was in Washington, D.C., and I just kind of was curious, you know, especially right now, how tall that spire is on the Capitol building. Could I do this to find out how tall it is? I don't have a chance in the world getting very close to measure that thing, do I? I think I'd probably get shot these days, right? I think the tensions might be a little high for people coming too close, right? So, you know, you can measure things at a distance, and that's actually kind of nice that we can do that. So I'm going to go ahead and stop right there for a little bit.